Hello and welcome to another video from sickmaths.co.uk, where you can find lots of free GCSE and A-level maths videos. This video is about integration for the C4 A-level maths module. It's actually part 2, that's why we're going to start from example 9. And part 2 of my integration video, that is. I've done a part 1 already. So this is my 9th example for the integration techniques, and we're going to talk about by parts, integration by parts. And the reason why it's called integration by parts is because you break your answer for an integral into two parts. One, the UV bit here, and then take away the answer to a further integral. So that's quite interesting. So the answer to one integral is equal to something minus the answer to a further integral, and I'm going to show you how that works. It's quite an easy technique, really. First of all, what you have when you are integrating by parts is two things multiplying each other, and you have to decide which one is going to be equivalent to u in this general formula and which one is going to be equivalent to dv dx in this general formula. Okay, so I'm just going to decide for now that u is equivalent to x and dv dx is equivalent to cos x, and that affects everything else in the answer, because then that will affect what uv is equal to and what v du dx is equal to, and basically what I'm going to integrate in the next part of this integral. So let's just go for it and you'll see what I'm talking about. So if u is equivalent to x and dv dx is equivalent to cos x, well then uv is going to be equal to, well, u is equivalent to x already, we know that, but what is v going to equal? Because we know what dv dx is equal to, or equivalent to, is cos x. So how do we get v from dv dx? Well, differential of v is dv dx, we know that. So the opposite, the integral of dv dx, is going to be v. So that means if we integrate this, we get what our v is, because this is supposed to be our dv dx. To get v, we have to integrate cos x, which is sin x. That means x sin x is basically our uv bit. Okay, now we have to take away, so take away because of this, and we find the integral of v du dx. So we know v, which we just worked out, is sin x, so put sin x there. And we know u is equivalent to x, so that means du dx is equivalent to 1, because the differential, that du dx means the differential of u, right? So we want to find the differential of x, which is 1. So that means we want to integrate over here in this second part sin x, because v is sin x, times 1. Well, sin x times 1 is just sin x, so basically you want to integrate sin x by dx, of course. So integrating sin x by dx gives you minus cos x, so the answer to this is minus cos x. So we're going to do x sin x minus cos x, which actually just means plus cos x. Minus cos x means plus cos x. So the overall answer to this is x sin x plus cos x plus c, of course, because when you integrate that you get a plus c. Very simple. Now, how did I decide that u should be equivalent to x and dv dx should be equivalent to cos x? Because if I wanted to, I could have said u is equivalent to cos x and dv dx is equivalent to x. Okay, and a simple reason is, when you try to find a solution to this, you get to a second integral. You need to know the answer to a second integral. Now, in the second integral, what you do to the u bit is you differentiate it. Now, ideally, when you come to the second integral, it should be a really easy thing to integrate, as was sin x. Okay, but if you choose the wrong value of u, for example, if I chose cos x instead, okay, then what I would get is something really complicated. Basically, I would have got what would I have got there? So if u was cos x, then I would have got minus sin x times, and the x would have been basically half x squared. So I would have got something really complicated as my second integral, and I got myself in trouble. Now, sometimes you can't avoid having a complicated second integral. Yeah, when I say second integral, I mean the second part of the by parts solution. Okay, so sometimes you can't avoid it, but why not make it as easy as possible? Now, by choosing u to be equivalent to x, when I got du dx, I just simply got 1. And that makes it really easy, because that becomes 1, which is basically nothing really, of no significance. And basically all I end up doing is integrating sine x. Yeah, so that's the ideal situation. So the top tip for integration by parts is to choose u as the simpler of the two functions that are multiplying each other. Okay, so that's that. Any other tips? Well, if you do get something really complicated in your second integral, I mean this integral here, okay, what you should remember is whatever the answer is, however complicated it is, stick it in one massive bracket, the answer, and make sure you have a minus in front of it, because some people forget to put the minus, they forget that we're taking away the answer to this integral. And yeah, and sometimes if it is complicated, you might have to do by parts again, which is not too surprising because you got two things multiplying each other. So yeah, sometimes you just end up having to do that. Now, the rest of this should be quite straightforward in that there aren't any further techniques to learn for integration other than just messing around with this differentiation sign and doing a bit of substituting, but that's all really. So, what do I mean by messing around with this differential sign? Basically, we're going to treat it like a fraction, and I'm going to move this dx to that side, and I'm going to keep this dy bit over here. And basically I'm going to try to create an integral like this, and the way I do it is I move all the y stuff towards the dy over here. So I move this y up, makes it 3y. That was a divide by y, becomes a times by y, so 3y dy is equal to x minus 5 dx. So I've got the x's next to, or x's stuff, yeah, next to the dx, and I've got the y stuff moved towards the dy, which gives me this situation, 3y dy equals x minus 5 dx, and I put these integral signs there. So that's how, but this is what we're allowed to do. As soon as you got your integral sign there and there, you can stick a, so I mean, as soon as you got a dx there and a dy there, you can stick your integral signs there and there. Okay, and then all you do is you simply integrate those. So integral 3y is simply 3, so basically y squared over 2 times 3, which is 3 over 2 y squared, another way of saying it. Integrating that as usual gives you half x squared minus 5x plus c. You might be thinking, what about the plus c for this? Well, whenever you integrate, yes, you get a constant of integration, and we got a constant of integration there. And what we're basically doing by writing just 1 plus c there, we're saying there was a constant of integration there, and we brought that constant over there and took it away from the constant here, and combined those two constants combined to make that plus c there. So it's just a technique we use again and again. Once you get used to this idea, it's quite simple. Anyway, so we've basically got an equation, and actually the original question was to solve this. Okay, when you say solve this differential equation, as they say in the exams, okay, when y equals 2 and x equals 4, that means just create an equation, and this y equals 2 and x equals 4 is just there so you can work out what c is. You must have done this many times before. When you've got a letter you don't know, but you do know the values of the other letters, you just substitute for them. So I substitute y equals 2 there, and x equals 4 over here and there, and you know, multiply it out, and I end up finding out that c is equal to 18. So all I do is I change all of this to 3 over 2y squared equals half x squared minus 5x plus 18, as I've written here. Yeah, that's it really. There's more of the same stuff, okay, over here. We're going to mess around with the differential sign in the same way, and more substitution. In this case, I'll have more letters to work out, more constants to work out over here and here in a minute. That's why I've got more things to substitute to find them out. So you'll see what I mean in a second. Okay, so as before, I'm going to move the dt up there. So I'm basically separating the dp and the dt bit. Okay, now I want to move the p towards the dp bit because I want to integrate p by dp, not by dt, which the dt is moving here, isn't it? So what I get is 1 over p, because you can imagine there's a 1 over there and the p goes underneath, so it becomes 1 over p dp equals k dt, and I put integral signs as well, so that's what I get. Integral of 1 over p dp equals integral of k dt. Integrating both sides, I get, that gives me ln p, and this gives me simply kt, because k is simply a variable, a constant. No, not a variable, it's a constant. It's just a number basically. So when you integrate a number, you just attach the variable next to it, and you get the plus c. As I explained earlier on over there, we do get a constant of integration there and here, and combining those two constants of integration you get the plus c. So I moved that constants of integration on this side and it combines to make the plus c. Anyway, so you got this, and we've got to somehow work out c and k. So when I substitute t equals 0 and p equals 2, t equals 0 makes this disappear, and p equals 2 means ln 2 is equal to c, because that's gone already. So we worked out one constant already, so that's why I said here t equals 0, p equals 2 gives ln p equals kt plus ln 2, because we just worked out c was ln 2. Now, if I, and that can be rewritten by the way, if I move that ln 2 to the other side, I get ln p minus ln 2, which can be written as ln p over 2 using the laws of logarithms. Okay, so now I've got this neat little thing here, okay, which is a common trick, so you know, learn that trick, yeah, trying to squeeze it into one type packet if possible, rather than have it all spread out, yeah, like this, with ln 2 sticking out on one side. So anyway, I've got ln p over 2 equals kt, and now I'm going to substitute the next pair of numbers, so t equals 1 and p equals 4. Now, when you do that, t equals 1 gives you 1, basically makes that 1k, and when p equals 4 you get ln 4 over 2, which is basically ln 2. So ln 2 is equal to 1k, basically k equals ln 2. Okay, great, so both of them happen to equal ln 2. Don't always have to, but that's how it worked out. So basically now we've got ln p over 2 is equal to ln 2 times t, or t ln 2, like we've got here. And if I've got t in the front, what can I do? I can move that up like I've done here. So now ln p over 2 is equal to ln 2 to the power t. And the reason why I did that is because then I can compare them. The reason why I moved that t up is so I can compare this with this. Ln p over 2 is equal to ln 2 to the power t, therefore p over 2 is equal to 2 to the power t. Now, if that is equal to that, and we want to find out p when t equals 3, well, if I put 3 into there, this is what I get. P over 2 is equal to 2 to the power 3, because that's where the t was, as a power of 2, and 2 to the power 3 is 8, so p over 2 is equal to 8, and therefore p must equal 16. So, I know that's only one example, but they are all pretty much the same in this respect. When you want to solve this kind of equation, you're going to get two constants that you have to work out, and you get two pairs of numbers, and yeah, you do this kind of stuff. You move the t up there, you move the relevant letters towards the right sides of the equation, so p moved towards the dp. The k could have moved to the other side also actually, but there's no need to really move too many things, so it doesn't really matter which side the k was, because it's just a number, isn't it? But it's not a variable like p. Okay, but in this case over here, I kept the x's on the dx side and moved the y's on the dy side. That's all there is to say really about that.